Welcome back to Kinetics. We are on our last topic of this unit. We're going to talk about how temperature affects reaction rate, and specifically how temperature affects the rate constant, or K. Let's go. So generally, as temperature increases, so does rate, because K is temperature dependent. In order to have chemical reactions, the chemicals must effectively collide with each other. And remember that an effective collision is one that has sufficient energy and correct orientation. So not only are you putting the Legos together top to bottom, but then you're also clicking them, giving them enough energy to get connected. So before a collision, we have this green guy trying to knock into this molecule that's going that way, and then they knock and they have a collision, and then this one splits off and goes off to the other side. At higher temperatures, molecules are more likely to have sufficient energy, they're moving faster, and since they have sufficient energy, there's going to be a higher number of collisions. They're going to move so fast, they're going to hit each other more often. And since there's more collisions, there's a higher number of collisions that are likely to have correct orientation, or to be effective collisions. The more collisions you have, the more likely at least some of them will be effective. So the Maxwell-Boltzmann distribution will show us the number of molecules, or the fraction of molecules, that have this amount of energy. At any given temperature, there's a wide distribution of kinetic energies, but at higher temperatures, there's a larger proportion of molecules that have the higher energies. So this Maxwell-Boltzmann distribution, you have seen it before several times this year, hopefully. Notice that as the temperature increases, so does the number of molecules that can overcome the activation energy barrier. So at a lower temperature, it looks to me like the lower temperature is higher than the higher temperature, and so if we're looking here, I'm feeling like the lower temperature is higher, but we're looking at the wrong axis. It's not the fraction of molecules that have that energy, it's the kinetic energy that those fraction of molecules have. So instead we should be looking down here at the x-axis instead of the y-axis. The lower temperature is lower on the x-axis than the higher temperature is. So more molecules that are at the higher temperature have a higher kinetic energy. But either way, let's say this is the particular amount of energy required to get the reaction started, the activation energy. So at that activation energy, the higher temperature molecules have a larger fraction of molecules than the lower temperature molecules do. They only have this many, whereas the higher temperature molecules have this many. So the Maxwell-Boltzmann distribution looks a little bit tricky, but remember you're looking at the x-axis, not the y-axis. Now the Arrhenius equation is a formula for the temperature dependence of reaction rate constant, and therefore the rate of a chemical reaction. So how we're actually going to relate the rate constant to temperature. K is a constant that changes with temperature. Now, the College Board doesn't particularly care that you can solve this equation, just that K does depend on temperature. But we're going to solve it once just to kind of prove it to ourselves and see what it is. So first I want to look at the equations, or the variables. There's two different forms of the Arrhenius equation. K is equal to AE to the negative EA to the RT, which A is just an Arrhenius constant, E is the inverse of natural log, EA is the activation energy, R is the gas law constant, but in this case we're going to put it in joules instead of latmol, so it's 8.31, and then T is the temperature. Another version of the exact same equation, instead of using the inverse natural log, we've got the plain natural log. K2 over K1, that'll be two different Ks at two different temperatures, and then T1 over T2 are the two different temperatures. EA is the activation energy, and R is the gas law constant in units of joules per K mole. Let's solve this equation just one time so we can see how it works. So the denaturation of a certain virus is a first-order process with an activation energy of 586 kilojoules per mole. The half-life of the reaction at 29.6 degrees Celsius is 4.5 hours. Compute the half-life at 37 degrees Celsius. So I'm seeing a couple of units that don't match up, and the first thing I'm going to do is mess with the units. 29.6 degrees Celsius plus 273 is 302.6 Kelvin. 37 degrees Celsius plus 273 is 310 Kelvin. 586 kilojoules per mole times 1,000 is 586,000 joules per mole. So that's just the first thing I want to get taken care of, is have all the units match up. Now let's look at that Arrhenius equation. ln of K2 over K1 is equal to EA over R 1 over T1 minus 1 over T2. Now we're not using the other form of the Arrhenius equation because we have two temperatures and two Ks to solve for, so the other one only accounts for one temperature or one K. Now, K, that's going to be a rate law constant, which is not given anywhere in the problem. How can we solve for rate law constant? Well, remember that it's a first order reaction, and so half-life for a first order reaction is 0.693 over K. So I can actually solve for the different Ks using the half-life, since it does tell me what the half-life is. So for the first reaction at 29.6 degrees Celsius, the half-life is 4.5 hours. So using that, I could say K is equal to 0.693 over the half-life, 4.5 hours. 0.693 divided by 4.5 is 0.154 per hour. So that's my first K, or my K1. And now I'm just going to plug into this formula. ln of K2 over K1, 0.154 per hour, is equal to EA, that's the 586,000 joules per mole, divided by R, that's the 8.31 joules per K mole, times 1 over T1, that's the 302.6 Kelvin, minus 1 over T2, that's 310 Kelvin. And now I'm just going to start solving. We've got joules will cancel, moles will cancel, and this is per Kelvin on the bottom, so that's Kelvin on the top, which is going to cancel with these kelvins that are on the bottom. So all of my units on the right-hand side totally cancel out completely. I'm only interested in numbers. So solving for the numbers, 586,000 divided by 8.31. Let's see, ln of K2 over 0.154 per hour is equal to 70517 times 1 over 302.6 minus 1 over 310 is equal to 7.89 times 10 to the negative 5. And we already canceled out the units, so I don't have to worry about the units anymore. So multiply those guys together and you get 5.56. So now, ln of K2 over 0.154. To get rid of a natural log, we're going to take e to the power of. So we'll say K2 over 0.154 per hour is equal to e to the 5.56. E to the 5.56 is 260.56. K2 over 0.154. 0.154 per hour is 260.56. All right, now let's take it on to a new slide so we can kind of see what we're doing. I'll rewrite that. So K2 over 0.154 per hour is equal to 260.56. Multiply both sides by 0.154 per hour, and I have K2 is 40.12 per hour. Oops. Try that again. Okay, here's the problem. It's not asking for K2, it's asking for the half-life. So remember that half-life is 0.693 over K, and K is 40.12 per hour. 0.693 over 40.12 per hour is equal to 0.017. Hours are on the bottom of the bottom, so plain normal hours. That's my second half-life. Now, what's important about that is that I increased the temperature by 7 degrees C. Temperature increased by 7 degrees C. Half-life went from, let's see, 4.5 hours to 0.017 hours. I increased the temperature by only 7 degrees, and the half-life, the amount of time it takes to cut the reaction, concentration is half, is now 0.017 hours. Hold on 17 times 60. That's like 1 minute. So it went from 4.5 hours to 1 minute to get rid of half of this virus. Which is why you want to, wash your hands with hot water, because it'll kill more bacteria, and it'll make the half-life of that bacteria much, much, much smaller. So that's how temperature will affect reaction rate. And there's your Arrhenius equation. Remember that the College Board doesn't want you to actually solve it, they just want you to know the relationship between K and rate. And even a small temperature increase can increase the reaction rate significantly. There you go. That was kinetics. I hope you had fun.